Okay, we're going to talk about Taguchi today. And before I start talking about Taguchi, first I'll tell you that Taguchi is popular in industry, but sometimes traditional statisticians, they don't like it. They think that Taguchi is not, theoretically sound statistics. But for me, I'm the opposite. I would like to show you why Taguchi is good, because we all agree, right? 2 to the 2 to the 3 to the 4. Just when you have so many levels, so many factors, sooner or later this thing's gonna out of control. It's very, very hard to design experiment for it. And so what Taguchi did is basically try to find some mental shortcut. Try to basically as mean as lean as possible. Try to make the whole things quick and dirty. But because it's quick and dirty, sometimes, it's shortcut. So people hate it because not enough statistical background behind it. Okay? And what will be the solid way to do this? Be honest, is the random effect, fixed effect, and then try to figure out the whole things by evaluate those factors one by one. Okay, so fractional factorial design, and then with random effect and fixed effect, that is what we covered in the last 2 weeks. Those are the right way to do things. But on the other hand, I'm upload one paper I did when I worked for industry. When I work for industry, a lot of time, guess what they want? Give me the answer. Just tell me, should I make this, slide or this, whatever, this big or this big? Give me the answer. Even though I know that it's not statistically rigorous. And if you ask me, can you use random effect, fixed effect to get that done? Yes, you can. Just if you try to do it the right way, it's a lot of work, and then costs a lot of money. But on the other hand, if you use this approach, it's kind of like it provides some backdoor for you to get things done quick. When you try to get things done quick, that, So why I'm telling you this is, okay, I show you this is if you have a very, very complex situation, but then your boss just give you the mission impossible. Give me the answer, and I'm only give you 1/10 of the budget and time. Get it done. And so the weakness of this sometimes is quick and dirty, but the advantage of it is quick and dirty. You guys follow me? Yeah. So why I choose to talk about this at the end of the semester is for that reason. Okay. So Taguchi basically said that if I have a lot of variations, okay, and then I'm looking, for example, so I can have my input in this area, but my output will have this much of variation. But if I move to an higher area, not only I can get a better performance, also less variation. So Taguchi basically tried to say that if I have random effect or fixed effect, I try to do two things at the same time. Okay? So for example, this example here, okay? And let me say, I have design A and design B, okay? Say it's for a car, gas mileage. And look at this. Gas mileage for design A in Boston, New York, San Francisco, Chicago, DC, Houston, Dallas, Miami, and Atlanta. I tried this in different cities. So this is my blue design, and you can tell on average The blue design, the gas mileage is 26.6 miles per gallon. And then design B is 25 miles per gallon. Okay? So obviously design A is better than design B based on the average, right? But if you look at the performance of this whole things, red design is design B, blue is design A. Which one you prefer if you're buying a car? Huh? The which one? The red one or the blue one? The red one. Why the red one? So the performance is consistent. So robustness, by definition, is insensitive to the variation. So in this situation is that generally red one is a lot more consistent, so the variation is a lot smaller. Okay? And the blue one is sometimes good, sometimes bad. So the thing is that Taguchi tried to mix these two things together. Okay? And said at different city, it's almost like have different judges, human factor. And basically said, I don't know what will happen in the future, who I'm going to encounter, what kind of situation I'm going to encounter, but I would like to generate enough situation to see if I can have a performance not only good, but consistently good. That's how robustness is defined, or basically is insensitive to the variation. Okay? So I'm going to show you how to do the computation, but first let me give you a paper of mine, probably 20 years ago. But this is a paper I did when I worked for industry. This is the Taguchi knife design. Okay, yeah, 1997. Not 20 years. Yes, more than 20 years, right? Not 25 years. Oh, next year. Okay, it's 25 years. Long time ago. Okay, and why we're doing this? Okay, you guys know what is carpal tunnel syndrome? Yeah, and this is getting a little better. Okay, for a while, all the snakehead, they will let migrant worker or meat packaging plant, okay, controlled by three major chain. They will smuggle people across the border, past the Rio Grande, and then give them a fake green card, and they start working. So meat packaging plant, very few workers are unionized. Even today, it's still the case. And what happened was that a lot of time people will have laceration, have all kinds of injury, and once they injure, okay, and become a big problem. And the problem is that even now, okay, the immigration law basically said that the employer, they don't need to verify if your green card or your social security number is real or fake. As long as you give me a green card, a social security number, I hire you. The verification is government's duty. But then, let's turn around. Guess what happened when those workers survive? They try to bring their wife, their family here, and a lot of time become a burden to, especially Midwest, a lot of small town. Meat packaging plant right next to a school district that they need to hire a teacher for English as second language, and so become psychosocial economical issues. And what we're trying to do at the time, basically just try to come up with different design of knife to help the workers, to get their performance done well. A couple of things we did, okay? At the time, we have the so-called mesh gloves, and then we let them wear two layers of gloves, latex and then mesh gloves to protect their hand. And then we also, teach them how to sharpen their knife. But what is really hard is we try to design a knife for them that to minimize the wrist movements. Okay, and so at the time there is a type of knife called piston shape. It's a bended knife, and considered is the one to reduce the carpal tunnel syndrome. But what we found is that still people complain about it and got lacerations and everything. Oh, have you guys ever read the novel The Jungle? Well, you can read it. It's about meat packaging plant in Chicago in the, before the 1920, 1930. And of course, during that time, the migrant workers are not from the South. It's from, Ireland, Italian. But the story is the same, right? You push them, and then sooner or later they get injured. And for me, work for an insurance company, my job is not getting involved into the psychosocial economical issue. My job is try to figure out what kind of tool I can provide to be safer and not reduce their productivity. So the knife design basically we come up with was several things we changed. Okay, first, so here's the knife design. We have different grip size, the circumference. Okay, if it's too big, it's not easy to hold, but it's too small, the control is bad. So what would be the right range? So we have different circumference in oval shape. And then we have the coupling angle, 90 degree, it's a piston shaped knife, or 45 degree, somewhat curved, and then 0 degree straight knife. Blade height, the taller the knife, the better, the smoother the cut, because better glide, but more frictions. So here are the blade height, and then finally the blade length. Longer knife is like a Zorro's sword. If you move your wrist a little bit, the tip of the sword move a lot. But on the other hand, if you have a handle very, very long, but the blade is very, very short, then it's kind of like a surgical knife. You move your wrist a lot, but the blade only tip a little bit. So one is good for piercing, the other one is good for gliding. So now, if you really look at this kind of experimental design, 3 by 3 by 3 by 3, how many design you need to have? 81, right? But Taguchi basically come up with a orthogonal array, says that we only use certain combinations, not all of them. So totally, I only do 3 to the 4 minus 3. I only have 9 design. Rather, 3 to the 4 minus 2, only have 9 design, rather than doing that many design. Okay, and then on the random effect, that's the tricky part. Taguchi basically said that random effect, remember the random effect is supposed to be random, right? But his argument is that, but if you know that the random effect got certain range, let's just pretend we're giving the random effect, but the random effect really is a kind of like upper bound and a lower bound. And so let me see how my design can survive those conditions. So the things what we did is this. Rather than ask people to cut the steak or ice cream, this time we just asked them to cut architecture clay. And why we're using clay? Because we can control the temperature and the thickness. So every cut can be experimentally designed. And then we asked them to cut a figure 5. Anybody knows why we asked them to cut a figure 5?
It's got kind of all the different shapes that you would want.
Yeah, one horizontal cut, one vertical cut, and one circular cut. And so our job is to see how many clay can they cut as fast as possible. But the random effect is, I have to, just like a car, right? Car have different engine, different transmissions. Now I have knife. I have to have, remember I have Boston, New York, different city. Now I just have different clay design to let them cut. So sometimes the clay got room temperature, the other one is frozen temperature. So you know that frozen temperature is a lot harder to cut, right? And then clay thickness. The thicker the clay, the harder to cut. And then finally, the clay orientation. We let them have 0 degree and 30 degree by changing the tilting angle. So when we do this, the argument is, again, the same thing. Different design under different conditions. We can compare the mean, we can compare the standard deviation. So the job is try to figure out which car got best gas mileage. Now is which knife on average can give me robust cut. Means what? I cut a lot, but without variation. So why? Because in the real world, even though you're using the machine, the stakes is sometimes thick, sometimes tendon, all kinds of surprise. So we're basically saying, let me create 8 different surprise, 2 by 2 by 2. Okay, so the things I would like you to remember is that Taguchi kind of like fake it here. This is supposed to be random effect, different situation. But he said that let me just push the boundary, come up with this different situations. But then, so they are not really random. But this not so random effect, I consider is random enough. I would like to see which knife can be good and consistently good. You guys follow me now? So, in order to do that, okay, Taguchi come up with a term called signal-to-noise ratio. And what is signal-to-noise ratio? Okay, and I'll come back for this. Okay. Yeah. The signal-to-noise ratio are these 3 equations. Okay. Okay. The equation is basically for smaller is better, larger is better, and the target value is better. Where is that? Oh, here we go. Okay, and put it this way, you can consider this is signal-to-noise ratio. It's almost like mean variance square. Mean square over variance. And then because they oscillate a lot, so you take a log 10. So if signal processing, this is basically is the same equation as signal processing, except that we're not measuring decibel, we're measuring the variation change of this. So I give you the equations here, showing you how to do the computation. So I have a situation. I can measure the average. I can measure the variance. And I can also measure if smaller is better or larger is better. And using those equations. And one thing is very interesting here is people, look at this, okay? When I try to measure smaller is better, or I try to measure larger is better, no matter which situation I used, sometimes no matter you're measuring larger better or smaller better or targets better, guess what? You end up with the best design with the best signal-to-noise ratio, the best one that you will choose, no matter what, is the same design. Can you speculate why? Because for the smaller design or bigger design, okay, they all have this uneven distribution, sometimes good, sometimes bad. And then you will have a robust design. It's kind of like somewhere in between and always reasonably good. And you can consider this, okay? Would you like to have a Corvette? I do, right? And I would like to get a muscle car to play with. The problem is muscle car is not very comfortable, and in a busy traffic jam, it's a lot of trouble, right? Would you like to have an F-250 or F-350 four-wheel drive pickup trucks? Same things, very good for the back row, but it's not very efficient on the freeway. And then, because the center of mass of the pickup truck is so high, actually it's quite dangerous when you have a sharp turn in high speed. But on the other hand, let's just say that the traffic situation is never, so in other words, if I'm only driving in the back row, I know F-250 is a good car. If I'm only driving, say, Montana and play on a freeway in the springtime, Corvette is a good car. But if I have, sometimes traffic situation, sometimes a little bit bumpy road, a little bit of everything, then I probably would get, a Toyota RAV4. Not very, very good in one situation, not very, very good in the other situation, but reasonably good in every possible situations. Okay? And so, Camry was designed that way. And guess which car followed the same design principle in the 80s, kind of like gained the U.S. market back? Ford Taurus. Taurus for a while is the kind of car is kind of like reasonably good under various situations. The signal to noise ratio is okay. Okay, and part of the reason is that Ford at that time they have a American Supply Institute. They get Taguchi and his son back to talk about how to do the experimental design this way. Okay, and then after that, okay, both lost the market for a while. Guess which car company dominated for a while? It's one of the big three in the 90s.
Was it GM?
Nope. Chrysler Caravan. Soccer mom and soccer dad, they suddenly realized that, not too big, not too small. It's just good enough for everything. So here I give you the equation, show you how to do the computation, to signal to noise ratio. But, by the way, but you guys can tell, right? Now, most of the car today, nobody's pure blood. What I'm saying is that you open the Toyota, there are a lot of stuff made in USA, but similarly, you look at any American car, Ford, GM, you will see a lot of, Mitsubishi, Honda, or I can't remember. There's a Mercury. They share exactly the same engine as yeah.
My first car and the car my mom drove and had the same engine, and I drove a '99 Chevrolet Prism, and she drove a 2000. She had like a 2004 Chevrolet.
Prism got a.
Yeah, she had a 2004 like Toyota Corolla, and I was actually able to my door handle. Well, the 1999 Toyota and the 1999 Chevrolet Prism, they had the same body. The only thing different was the engine. And so my door handles broke all the time, so I used to go to like car junkyards and get door handles off of Prisms and Corollas because I could use them both.
Yeah, because a lot of time is because of the supply chain. But I will tell you that argument gonna be gone very soon. This Omicron, who knows what it'll do to the supply chain. But now people start try to figure out how to have the design less sensitive to the disruptions. The other thing is that this happened even 2 years ago when people argue about the chip design. Biden now tried to force Samsung and a Taiwan chip manufacturer, to start manufacturing Intel chips in Arizona again. Why? Because nobody want to have your critical infrastructure or your car manufacturer and says that you cannot sell your car, you cannot get your car out of the assembly line simply because you don't have the right chip. So situations change again. But for a while, nothing is pure. And if you guys even look at the airplane, okay, the Boeings and Airbus, the entire airplane, the fuselage, the engine, everything's from different part of the world. How to find a robust way means that the tolerance is just right enough to piece everything together, not too tight, not too small, and that was the design philosophy. I can even tell you this argument, although is based on Deming's principle. Guess what is another success story? Not from U.S. or from the capital free world. It's from the communist country. During the Cold War era, which kind of rifle is really, really popular among the communist country, also among the third world country? Huh? What have you guys ever heard AK-47? Yeah. Why AK is better than say M16 or M14? Huh?
Simple construction.
Good job. It's because if you look at the design, the machine, everything's American rifle is much, much better. But the problem is that because it's so delicate, that becomes what? Not robust, sensitive to the environmental change. So you could be in the desert, you could be in the South Indochina's desert rice paddy field. If your gun is easily get jammed, or when you jump out of the helicopter, easily get bent, then you're even though you have the best gun, but it's highly require a lot of maintenance. On the other hand, AK is what kind of design? Simple. You dump it into the mud, dump it in everything. You can tell the gun is not as accurate as the M16 or M14, right? It's not that good. But on the other hand, the survivability under all kinds of situations is much, much better. So now you turn to the gun market. If you're bad guy, you're some guerrilla or whatever working in the jungle and trying to destroy everything, which kind of gun would you like? A highly accurate M16 or just get an AK to do the jobs? Weapon is definitely just to do the jobs, right? So that kind of philosophy is embedded in a lot of weapon design because weapon is only used once. But I will tell you that today, because of the whole world change, mass customization is the future. In other words, is that how to come up with a core design, and people can add stuff to it, and so everybody want to start, a small business for using internet, right? So what you want is that, I'm building this laptop platform. Here are some core robust design, but you can add different stuff to it. I can have a Segway or a skateboard, motor skateboard, or scooter, same things. What will be the good one? Is the one that I have a very, very simple core design, but you can add different cabin, different seat, different wheel. It's the same thing, but can be adaptive to all kinds of attachment. So what I'm trying to say is that I'm pretty sure you guys who can predict the future? Nobody can. But you guys gonna face a world that, how to have mass customization, come up with a core design to fit into different attachment. That I consider you cannot avoid. Okay, and now let me go back to the paper. I would like to show you a couple of things in the design. This is the computation. Okay, I already gave you the Excel spreadsheet, but now I would like to show you a couple of things. Okay, first, okay, if you look at the average, okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 9 different design, okay, you can tell, okay, design 9 is very good, design 5 is okay, design 2 is okay, but on average, design 9 is the best design, right? The bar chart shows this way. But if we base on signal to noise ratio, number 5 is the best design. Okay? And can you guys tell? Now, if I just say that, trust the Taguchi's computation, that's not the purpose, right? Even my customer would like me to have some explanations. So, to have the explanations, we detailedly compare the 9 different design, design 5 and design 9. And you can tell, okay, sometimes design 9 is not as good. Sometimes design 5 is not as good. But generally speaking, which one you can see more oscillation. 9 got extremely good, extremely bad, negative, positive, compared with design 5. And then if I try to figure out what's going on, this is my invention, okay? And the invention is this, okay? If I have the grip size, and the grip size, under different clay temperature, it vary a lot, vary not too much. So generally, you see that small grip size is not good. Medium grip size and large grip size, I don't know which one's better, but seems like grip size doesn't do much to the challenge of the temperature. But if you look at the grip size versus the clay thickness, very thick, not very thick, very thick, not very thick, you can tell that when the grip size somewhere in the middle, the variation, what I call this H chart. See, the H horizontal is pretty flat. And if it's very flat, means what? I don't care. You give me a thick steak or a thin steak, my medium grip size will be what? Robust enough to the grip clay thickness. You guys, can you tell that? Same things. For the clay orientation, the clay can be 30 degree or 0 degree. Okay? Small grip, sensitive. Large grip, a little bit sensitive. But in the middle is not sensitive. So I would say, the champion for the grip size, probably the middle is a good one to use. Next, coupling angle, right? I can have a straight knife, 45 degree pistol knife, or a 45 degree knife. Sensitive, sensitive, sensitive. Sensitive, sensitive, not so sensitive. Sensitive, maybe. So at least if coupling angle, 45 degree, can do anything, which one will be the one I'll use to deal with the challenge? Is using the 90 degree for the clay thickness. Okay, so now you see I'm not just talking about, have different design, different challenge. I start looking at which challenge, under which condition I can be insensitive. So here on the blade height, okay, large variation, somewhere in between. And again, blade height is very, very good to handle the clay thickness. This is pretty easy to visualize. If I have a very, very thick turkey, do you want a thin knife or you want to have a butcher knife to chop it? So you know that blade height is good for the clay's thickness. And then on the clay orientation, straight or you can tell these two are insensitive to the orientation. Finally, on the blade lengths, somewhere in between. So small and medium, I have a pretty good to handle the clay thickness and clay orientation. So now I can go through this one by one and tell my client, okay, hey, we should take design 5 or design 9 under which conditions. And one by one, if I compare the coupling angle, compare the grip size, sooner or later, okay, I can not only let the signal to noise ratio decide which one is good for me, I can actually do some fine tuning. So at the end, I will come up with a hybrid, not design 5, not design 9, kind of somewhere in between, take advantage of both sides to come up with a better design. Okay? And this is the approach we use to solve the problem. Okay? Now, finally, let me show you what in the field people usually use, okay, is they will come up with this so-called orthogonal array, okay, to cut down the number of experiments. That's not it. Here we go. So here are some cheat sheets. You might need it for your in the field. If your boss says that, hey, are you kidding me? You're gonna have 2 to the 5 times 3 to the 2, 300 different combinations to run the experiment? No way. And then you say, okay, let me do fractional factorial design. Let me do response surface. But no matter what you said at the end is what? Too much. So you just have to, at the end, surrender to your boss and say, okay, let me come up with a quick and dirty way to do this. And so here are some quick and dirty approach. He basically said that, okay, 2 to the 3, he only used 4 experiments. Okay? And so it's always fractional factorial. 2 to the 7. 2 to the 7 is what? 128. He only used 8 different experiments. So every time when he used a fraction of it, okay, to come up with the combinations and then come up with the challenge and say, oh, what's my signal to noise ratio? You will get an answer. At least you can say, oh, just follow like my knife design approach. Because think about it, if you do the knife design purely, okay, under different conditions, will be 81 different knife design times 8 different fixed conditions. That's what? 644 different design, experimental trial. And with repetitions, I don't believe any customer will support me to do that. Okay? So how to come up with a very, very quick and dirty way to get things done. This is the table he used. Basically, he just says that whatever the fractional factorial design, I'm only using a very, very, very small fraction of it to come up with the design, and then under a different challenge, okay? And two level, 3 level, 4 level, and so on. Okay, here is the 3 to the 4. This is the 81 I use. If you compare, my experimental design is using L9. He called it L9. Basically, is 3 to the 4 minus 2. 9 of the design. Okay, and from an industrial engineering or system engineering standpoint, would you get an answer? This approach, you always get a quick and dirty answer, okay? But can you use this to write, say you want to go for grad school, can you use this for a PhD dissertation? No. If you do it that way, you're not trying to prove something. You're trying to, ask your committee member to reject your proposal. Okay, so this is the drawback of this whole thing. But Noah, then tell me, if this is so bad, why I introduce this at the end of the experimental design class?
Because it's probably a little bit more realistic than what we're talking about with like working on a dissertation where you had to do all the statistical methods and proving. With this shortcut, this is going to be a better way for us to get an explanation in a practical setting.
Yeah, and the other thing is that sometimes I'll use this as a pilot study. Because if I can show my boss, hey, there's something here, okay, then maybe he will say that, okay, let me compromise. I'll give you half of the budget you asked for, okay? And this is the kind of things that I have to let you guys know. If you try to be very, very loyal to statistics, to p-value, and sometimes you cannot get do your job. And so, I'm trying to say that this is not a scientific way, but it's a good enough way to get started. Okay, this is the reason why I'm having this, showing you this. Okay, so I think I finished this semester. Okay, so everybody think about it. Okay, and we started by central station, subway station for treatment, and then we start saying that we can block them so we don't have to do everything in one shot, and then we start dealing with factorial design. And when we do the factorial design, we focus on the high-low two-way factorial design. Why? Because, at least they can show the contrast. And then we use the regression approach. We use the pseudo-variable approach to show you how those tables are built. And then once you can follow the two-way design, we go to the three-way design. Three-way can be considered as the two-way twice. And once you have the two-way and three-way done, I start saying that, okay, now most of the situations you should be able to handle in a rigorous way. Then how to provide the legal documentation when you finish your experimental design, your ANOVA table, your multiple comparison as your IID assumption, independent, identical, the Durbin-Watson test to make sure those things are good. And once we finished the factorial design with the blocking and everything, we said, okay, the world is very, very complex, and you have so many things you have to study. You don't have the money, so we do fractional factorial design, try to chop it down and use blocking. And then when you do that, you'll make a lot of assumptions So we have to come up with a step-by-step way to check those things, okay? And once we declare, we finish all the factorial design, we said, how can I use a factorial design for response surface investigation to find the maximum, minimum, or the saddle point? But when I do that, I'm only using a 2x2, a square dance. In a real world situation, you could end up with a multi-factorial design again, and very, very complex. You still can do your response surface design. When you do that, okay, you have to consider that the investigation require a lot of money, a lot of time. So the thing is that for COVID vaccine, probably the pharmaceutical company will have the CDC blessing and use tons of money to do that. Actually, the guy who come up with the design, the BNT, he did not get enough money. That's how Pfizer took over his design, because he just doesn't have enough money to investigate that. Okay, so now I'm introducing the Taguchi. I just want you guys to think about it. Can you use fractional factorial design or Taguchi in response surface investigation? Can you? Yeah, why not? You just, basically quick and dirty every step until you find a reasonable max or reasonable mean. Okay? And I would say that it's always, the balance between two devils, right? You want to be rigorous, you want to be scientific, but at the same time, you still want to get the job done. So a lot of time, you surrender to the reality and figure out how reliable your optimum is good enough to get paid. Okay? So that concludes this semester. And on the random effect model and the what I call that the hierarchical part and Taguchi, I decided not to give you any homework because I think you already have a pretty labor-intensive third exam. But this material I cover at the end. Keep it in mind. You're going to encounter this for sure in the future. Okay, that's the end of the semester. Thank you.